Have you ever, hit send on an email and then immediately wondered, is this going to end up in spam? Or maybe worse, did that dodgy bank statement email actually slip through your filter? Or perhaps you just want to get your head around some, well, frankly complex ideas without needing a PhD first. If so, you are absolutely in the right place.
Welcome to the Deep Dive. This is where we sift through stacks of information, articles, research, you name it, and boil it down into insights you can actually use. Today, our mission, should you choose to accept it, is a deep dive into two real superpowers of machine learning: classification and regression. Think of them as, a dynamic duo. One sorts things into neat boxes, the other predicts numbers. We're going to unpack it all super simply, because learning this stuff should be fun, right? Not a chore.
Absolutely. And underpinning both of these is this key idea called supervised learning. Just imagine learning something new, but you've got this amazing teacher right there with you, giving you examples, giving you the answers. That's basically supervised learning. It learns from data where we already know the answers, or the labels as we call them, like showing a kid a picture of a cat and saying cat. The picture is the data, cat is the label.
Precisely. The picture is the input, cat is the label. You got it.
That makes sense. But even with that guide, that teacher, can things go wrong? Can biases sneak in from those right answers? Teachers aren't always perfect, are they?
Oh, that's a really important point. Yes, absolutely. The quality of your labels, your teacher, is everything. If your training data is biased or maybe incomplete or just plain wrong in places, well, your model is going to learn those flaws.
Ah, the old garbage in, garbage out problem.
Exactly that. It applies directly here. The data you feed it is crucial.
Okay, crystal clear. So, with that foundation, let's jump into the first superpower, classification.
Right, classification. So at its heart, it's really just about sorting things, putting them into distinct bins or categories. Think about sorting your laundry. You've got your darks, your lights, maybe delicates. You're not asking how much they weigh.
No, you're just putting them in piles. Darks pile, lights pile.
Exactly. You want a specific label, not a continuous value.
So it's not how spammy is this email on a scale of 1 to 10. It's just spam or not spam, yes or no?
Precisely. Or, will this patient have an adverse reaction? Yes or no? What grade will you get? A, B, C, or D? Those are labels.
Got it. Distinct categories.
And you'd be surprised how common this is. There are different types, too. You've got binary classification. That's a simple one. Just two choices. Spam, not spam. True, false.
Okay, two options. Big sense.
Then there's multi-class. Lots of possible labels, but only one can be right for any given thing, like identifying an animal as a cat or a dog or a bird. It's usually not all three.
Chuckle slightly. Unless it's a very strange pet. Okay, multiple choices, but only one answer.
Then you have multi-label. This is where multiple labels can apply at the same time. Think about tagging a photo. It might have a beach tag and a sunset tag.
Ah, okay, so one thing can belong in multiple boxes simultaneously.
Exactly. And finally, there's a really important one, the imbalance scenario. This is where one category is super rare compared to the others. Think about detecting credit card fraud. Most transactions aren't fraud, right? Hopefully.
Oh, funny.
So if your model just learns to say not fraud all the time, it'll be incredibly accurate, maybe 99.9% accurate.
But completely useless. It misses the one thing you actually care about, the fraud.
Precisely. It's like that doctor we mentioned, predicting no one has a rare disease. Great accuracy, terrible outcome if you actually have the disease. The cost of missing what matters is too high.
So accuracy isn't always the goal, or at least not the only goal. Okay, so how do these machines actually do the sorting? What's the simplest approach?
Well, the absolute simplest has got to be nearest neighbor, NN for short. And the learning part, it's almost funny how simple it is.
Oh.
It just remembers. It memorizes every single example that's ever been shown in the training data.
It's just, and it sounds less like learning and more like, well, just having a really good memory. Is there a catch? A downside of being so simple?
Oh, there's definitely a catch. But let's see it in action first. When a new thing comes along that it needs to classify, it finds the single closest example it remembers from its training data, the nearest neighbor.
Okay.
And it just gives the new item the same label as that neighbor. It's like looking at someone new and saying, you look most like Bob over there, so you must also be a Bob.
Okay, let's try an example. Say we're classifying animals. Reptile, or not reptile. We've shown it loads of animals and their labels.
Okay, sounds good. So along comes a zebra. Our NN model looks through its memory, finds the closest animal it knows is, let's say, a guppy.
A fish, definitely not a reptile.
Right, so the guppy is labeled not a reptile. Therefore, the zebra gets classified as not a reptile. Seems reasonable, right?
Yeah, zebras aren't reptiles. Okay, makes sense so far.
Now a python slithers in. NN looks. Its nearest neighbor is a cobra.
Cobra's a reptile.
Yep. So the python gets classified as reptile. Perfect. NN is nailing it.
Seems too easy. What's the catch you mentioned?
Here it comes. What about an alligator?
Okay, alligator. Definitely a reptile.
Our nearest neighbor model searches its memory palace,
Hmm?
finds the closest match, and it turns out to be a chicken.
A chicken. You're kidding.
Yep. So the alligator gets classified as not a reptile because its nearest buddy in the data was a chicken.
Oh dear. That is spectacularly wrong. What happened there? How did a chicken end up being the closest thing to an alligator? And more importantly, how often does this kind of weirdness mess things up in the real world? How do you even spot it?
Well, the how can be tricky, maybe in the specific features we use, like, I don't know, weight and number of legs. The chicken just happened to be numerically closer than, say, a heavy tortoise. But the problem is the core issue with simple nearest neighbor. That's the Achilles heel. One single oddball data point, one outlier, like our surprisingly close chicken, can completely mess up the classification. It's like letting the weirdest person on your street make all the decisions for the neighborhood.
The grumpy neighbor problem.
Exactly. And in the real world, this could be disastrous. A wrong medical diagnosis based on one unusual patient record. A genuine transaction flagged as fraud because it looks slightly like one weird past case. People spot it through careful testing, looking at the mistakes the model makes, and questioning weird results like the alligator chicken incident.
Okay, so one vote is clearly risky. We can't just trust that one nearest neighbor. How do we fix it? Do we throw out the alligator data?
No, we don't throw out the alligator. We improve the voting system. This brings us to K nearest neighbors, KNN.
K nearest neighbors. Okay, what's the K?
Instead of looking at just one nearest neighbor, we look at K nearest neighbors. K is just a number we choose, usually an odd number like 3 or 5 or 17.
Why odd?
Good question. To avoid ties. If you look at 2 neighbors and one says reptile and the other says not reptile, who wins? With 3 or 5, you'll always have a majority vote.
Makes sense. Crowd wisdom, democracy for data points.
Exactly. So back to our poor alligator. With KNN, maybe we look at its 3 nearest neighbors. K3, maybe that includes the chicken, fine. But maybe the other 2 are a cobra and a boa constrictor.
Both reptiles.
Right. So now the vote is 2 reptiles versus 1 non-reptile. The alligator gets correctly classified as a reptile, much more robust.
Okay, that feels much safer. It smooths out the influence of those weird outliers, like the chicken.
It does. But it raises a new question. How do you pick K? You said 3, 5, 17? Can you just pick any odd number?
Right. If K is too small, like 1, you have the original problem. But what if K is huge, like you ask all the neighbors?
Well, 2 problems there. First, if K is really big, it can take a long time to calculate, especially with lots of data. You have to find and compare distances to many, many points.
Okay, computationally expensive. What's the second problem?
Remember our imbalanced data, like fraud detection, where most transactions are not fraud. If K is very large, and say 99% of your data points are not fraud, then chances are the vast majority of the K neighbors for any new transaction will also be not fraud.
So everything just gets classified as not fraud, even the actual fraud cases?
Pretty much.
Yeah.
A large K can just swamp the rare cases and always vote for the majority category, which, again, makes the model useless for finding the important rare stuff.
So there's a sweet spot for K. Not too small, not too big. How do you find it? Do you just guess?
We try not to guess. We use a technique called cross-validation.
Cross-validation. Okay, break it down for me. No PhD required, remember?
Smiling. Absolutely. Think of it like prepping for a big exam. You wouldn't just study using one method and hope for the best, right?
No, I'd probably try a few practice tests, maybe different study techniques.
Exactly. Cross-validation is like that for finding the best K. You take your data and you split it up. You use part of it for training, like studying, and part of it for testing, like a practice exam. But you don't just do it once. You shuffle the data and split it multiple times in different ways. You try out different values of K3, K5, K7, etc. on each of these splits.
And see which K gets the best average score across all those different practice exams.
Precisely. You pick the K that performs most consistently well across different slices of your data. It helps you find a K that's likely to work well on new, unseen data later.
Okay, that makes a lot of sense. Like finding the study method that genuinely works, not just the one that worked for one specific practice test. So KNN, pros and cons.
Okay, pros. Learning is super fast. You just memorize the data. That's it.
Easy peasy.
And it's quite intuitive to explain. The results are easy to understand. We classified this as blue because most of its nearest neighbors were blue. No complex math needed for the basic idea.
Right, you can picture the neighbors voting. What about the cons?
Cons are pretty significant, especially for big data sets. First, memory. You have to store all the training data points if you have millions or billions of examples.
That's a lot of memory. Your computer might complain.
It might indeed. Second, prediction speed. When a new data point comes in, you have to compare it to every single point in your massive stored data set to find those k-nearest ones.
Whoa. So classifying one new email could mean comparing it to millions of old emails. That sounds incredibly slow.
It can be, yes, very computationally intensive at prediction time, even though the learning was instant.
Okay, memory hog and slow predictor. Anything else?
Yeah, one more thing. KNN doesn't really give you a deeper model or understanding of why things are related. It just tells you who is close to whom based on the features you gave it.
So it tells you that the alligator is a reptile because its neighbors mostly are, but not why. Like, it doesn't learn that having scales or being cold-blooded are important features for being a reptile.
Exactly. It doesn't build an explicit model of the relationships between features and the outcome. It's purely based on proximity in the feature space. It gives you the what, the classification, but not really the why.
Okay, so KNN, simple concept, intuitive, good for some things, but memory hungry, potentially slow, and doesn't explain the why. What if we really want that why? We want to understand the factors driving the classification.
Excellent question. If you want the why, you often turn to other methods. And probably the most common, most workhorse classification algorithm out there is logistic regression.
Logistic regression. Okay, the name sounds a bit more statistical, less intuitive than neighbors voting. How does this one work? Is it related to regular regression?
It is related, yeah, but with a crucial twist for classification. You know how regular linear regression tries to predict a number, like a house price?
Yeah, it draws a line through the data points.
Right. But that number could be anything, positive or negative, huge or small. If you tried to use that to predict something like survived, won, or died, you might predict weird values like 1.5 or Medica 0.2, which doesn't make sense.
You can't be half survived. It's a yes, no, or a 0, 1.
Exactly. So logistic regression cleverly adapts the regression idea. Instead of predicting the number directly, it predicts the probability of the outcome being yes or 1. And probabilities are always nicely contained between 0 and 1.
Okay, so it might predict an 80% probability of survival or a 10% probability of an email being spam.
Precisely. And then there's usually a threshold, often 0.5. If the predicted probability is above 0.5, we classify it as yes or 1. If it's below, we classify it as no or 0.
So it gives a classification, but also a measure of confidence or likelihood. That seems really useful. You mentioned it helps with the why. How does it do that? You said something about weights.
Yes, the weights. This is the key part. Logistic regression works by finding a weight for each input feature, like age, gender, ticket class on the Titanic. These weights tell you how much each feature influences the probability of the outcome. Think of them like coefficients in an equation.
Okay, so each feature gets a score indicating its importance and direction.
Exactly. A positive weight means that as that feature increases, the probability of the outcome, like survival, also increases.
Yeah.
A negative weight means the opposite. As the feature increases, the probability decreases.
So maybe having scales gets a big positive weight for being a reptile, while number of legs might get a negative weight if we're talking about snakes versus insects.
Perfect analogy.
Yeah.
And the size of the weight, its absolute value, tells you how strong that influence is. A big weight, positive or negative, means that feature is a really strong predictor. A weight close to 0 means the feature doesn't really affect the outcome much, according to the model.
This is brilliant. This is the why. It doesn't just say reptile. It says reptile because it has scales. Strong positive weight and doesn't have many legs. Negative weight, maybe. It quantifies the influence of each factor.
You've nailed it. That's the interpretability, the insight that makes logistic regression so powerful and popular.
Let's bring this to life. You mentioned the Titanic beta set earlier. Predicting survival based on class, age, gender. How does logistic regression handle that?
Right, the Titanic. A classic if-saw-mer data set. We tried to predict survived, won, or died, 0, based on passenger features.
Now, we touched on this earlier, but it's super important here. The accuracy trap. What was the survival rate on the Titanic? Something like 38% survived, 62% died.
Roughly, yes. More people died than survived.
So a really dumb model could just predict everyone died for every single passenger.
It could.
And that model would be 62% accurate, which sounds Okay, but it's completely useless because it doesn't identify any of the survivors.
Exactly. It's the same as the no one has the rare disease doctor or the no transactions fraud detector. Accuracy alone can be incredibly misleading, especially with imbalanced classes or when the cost of missing one type of outcome is very high.
We absolutely need better ways to measure performance in these cases. What are the key metrics, especially for these life or death or maybe just high stakes scenarios?
Okay, one crucial metric is sensitivity, which is also known as recall. This measures how good the model is at finding all the actual positive cases.
So in the Titanic case, positive could be died, sensitivity would measure. Of all the people who actually died, how many did our model correctly identify?
Exactly. You want high sensitivity, high recall for things like cancer screening.
No.
You absolutely do not want to miss someone who actually has cancer, a true positive, even if it means you get a few false alarms, telling someone they might have cancer when they don't, a false positive. Missing a real case is the worst outcome there.
Okay, catch the positives. What's the flip side?
The flip side is specificity. This measures how good the model is at correctly identifying the actual negative cases.
So in the Titanic example, if died is positive, then survived is negative. Specificity asks, of all the people who actually survived, how many did our model correctly identify as survivors?
Right. You'd want high specificity if the cost of a false positive is very high. For example, deciding on risky surgery. You really don't want to perform surgery on someone who doesn't actually need it. A false positive classifying a healthy person as needing surgery. You want to be very sure about identifying the truly healthy people correctly.
So it's this constant balancing act, isn't it? Sensitivity is about not missing the positives. Specificity is about not wrongly flagging the negatives.
It really is. And the right balance depends entirely on the problem. We also often talk about precision and recall together. Recall is just another name for sensitivity. Precision asks a slightly different question. Of all the times our model predicted positive, for example, predicted someone died, how many of those were actually correct?
Ah, okay. So recall is, out of all who did die, how many did we find? And precision is, out of all we said would die, how many actually did?
You got it. They often trade off against each other. If you make your model really cautious about predicting died, your precision might go up. When it says died, it's probably right, but your recall might go down. You'll miss more people who actually died.
Choosing the right metric or combination of metrics seems crucial. It depends on whether it's worse to miss a case or to have a false alarm.
Absolutely fundamental. There's no single best metric for all situations. Context is king.
Okay, so we have these better metrics. How do we actually test a model like logistic regression to calculate them reliably? We can't just test it on the data it learned from, can we?
Good point, no. That would be like giving students the exact same questions on the final exam as they had in their homework. They'd seem brilliant, but you wouldn't know if they actually learned anything general.
Right, they just memorize the answers.
So we need to test it on data it hasn't seen before. We talked about cross-validation for KNN, and similar ideas apply here. For smaller data sets, sometimes leave one out, cross-validation is used. You train the model on all data points except one, test it on that one, then repeat the whole process, leaving out a different data point each time. You do this for every single data point.
Wow, that sounds incredibly thorough, like testing every single Jenga block's importance individually.
It is, but as you can imagine, it's very computationally expensive if you have lots of data. Training the model potentially millions of times.
Yeah, not practical for big data sets. So what's the alternative?
For larger data sets, we typically use something like k-fold cross-validation or repeated random subsampling. The idea is similar. Repeatedly split the data into a training set, say 80% in a testing set, the remaining 20%. Train on the 80%, test on the 20%, do this multiple times with different random splits, and then average the performance metrics like sensitivity, specificity, precision across all the test sets.
Okay, so multiple random practice exams, averaging the scores, gives a more robust estimate of how well the model will perform on genuinely new data.
Exactly. It's a standard way to get a reliable estimate of model performance.
All right, the moment of truth. We've got our metrics, we've got our testing method. What did logistic regression actually tell us about the Titanic survivors when we look at those weights?
Okay, so when you run logistic regression on the Titanic data, the weights paint a really clear and frankly quite stark picture. Being in first class, that got a significant positive weight, meaning holding other factors constant, being in first class strongly increased your probability of survival.
Okay, rich people did better. What about second class?
Second class also got a positive weight, but smaller than first class. Still better than the baseline.
And third class?
Third class got a distinctly negative weight. Being in steerage significantly decreased your probability of survival, according to the model.
Wow, so it's not just anecdote. The model quantifies it. Class was a major factor. What else?
Age. Older passengers had a negative weight, so increasing age was correlated with a lower chance of survival.
Okay, that seems plausible. And gender.
Gender was one of the most powerful predictors.
Yeah.
Being male received a large negative weight.
A large negative weight for being male. So the women and children first idea wasn't just a saying, it was statistically very real in terms of outcome.
Very much reflected in the data the model learned from. The model essentially quantified that social norms' effect on survival probabilities.
That's the real power here, isn't it? It's not just predicting who survived, it's giving us insight into what factors mattered most and quantifying their impact. The why behind the prediction.
That's exactly it. It moves beyond just sorting to providing understanding.
Incredible. Okay, so that's classification, sorting into bins, understanding the why with things like logistic regression. What about the other superpower? Predicting actual numbers.
Right. That brings us to regression. If classification is about putting things into categories, spam, not spam, reptile, not reptile, survive, survived, regression is about predicting a continuous numerical value.
So not, is this a house or an apartment? But what is the price of this house?
Exactly. Or what will the temperature be tomorrow? Not just hot or cold, but the actual degrees. Or how many units will we sell next month?
Predicting a number on a potentially infinite scale rather than a fixed category.
Precisely. The goal is usually to find a mathematical function, often visualized as a line or a curve, that best fits the historical data points so we can use it to predict future values.
You mentioned linear regression earlier, drawing a straight line. Are there other main types we should know about?
Yeah, definitely. Linear regression is the simplest. Finding the best straight line to predict one variable based on another, example, predicting exam score based only on hours studied.
Yeah.
Then there's multiple linear regression. Same idea, but you're predicting the outcome based on multiple input features. Like predicting a car's fuel efficiency based on its engine size and its weight and maybe its aerodynamics.
Okay, so incorporating more factors into the prediction, but still assuming the relationships are basically linear, just combined.
Right. But what if the relationship isn't a straight line? Think about plant growth over time. It might start slow, speed up, then level off. A straight line won't capture that well.
No, it's more like an S-curve or something.
Exactly. For those situations, we use polynomial regression. It allows the model to fit a curve instead of just a straight line, capturing more complex nonlinear relationships.
Like modeling my motivation to do chores throughout the week. Starts low, maybe peaks midweek, then crashes.
Chuckles.
Yeah.
That could work. And then there are more advanced types, like ridge regression and lasso regression. These are really clever.
Oh. What do they do? Are they about mountain ranges?
Not quite. They're mainly used to prevent a problem called overfitting. That's where your model learns the training data too well, including all its noise and quirks, and then doesn't perform well on new data.
Ah, like memorizing the homework answers perfectly but failing the actual exam.
Exactly. Ridge and lasso add a penalty to the model for having overly complex relationships, essentially, for having really large weights or coefficients. They encourage the model to be simpler and smoother.
Like telling the model, keep it simple, stupid.
Sort of. Lasso is particularly interesting because its penalty can actually force some feature weights to become exactly zero.
Wait, zero. So it just throws that feature out entirely.
Effectively, yes. Lasso can perform automatic feature selection, telling you which of your input variables aren't actually helpful for the prediction according to the model. It simplifies the model by discarding irrelevant information.
That's really cool. The model cleans itself up.
Yeah.
Okay, so we have these ways to predict numbers. How do we know if the prediction was any good? We can't use sensitivity or precision, right? Those are for categories.
Correct. We need metrics that measure how far off our numerical prediction was from the actual value.
Okay, what are the main ones?
Probably the simplest is mean absolute error, MAE. You look at the difference between your prediction and the actual value for each data point. Take the absolute value, so errors don't cancel out,
Yep.
and then average all those differences.
So if you predicted a house price of $300 and it sold for $310, the absolute error is $10. MAE is just the average of those kinds of errors across all your test houses. Simple, interpretable.
Very easy to understand in the original units, like dollars or degrees.
What else? You mentioned penalties earlier.
Right. Often we care more about large errors than small ones. Being off by $100 on a house price is much worse than being off by 1K, right?
Definitely.
So we use metrics like mean squared error, MSE. Here, you calculate the difference, then you square it before averaging. Squaring makes the bigger errors have a much larger impact on the total score.
Ah, so that $100 K error becomes $10 billion in the calculation, while the 1K error only becomes $1 million. It really penalizes those big misses.
Exactly. The downside is the units become squared,
Yeah.
like dollar squared, which is weird to interpret. So we often take the square root of MSE to get the root mean squared error, RMSE.
RMSE. So that gets you back to the original units, like dollars, but it still penalizes big errors more heavily because of the squaring step inside.
You got it. RMSE is very commonly used. It gives you a sense of the typical error magnitude, with extra weight given to larger errors. I remember a project where focusing only on MAE hid some really bad occasional predictions. Switching to RMSE immediately highlighted the problem because those few huge errors dominated the score.
Good lesson. Penalize the big mistakes. Is there anything else?
One more common one is R squared, sometimes called the coefficient of determination.
R squared. Sounds familiar from stats class.
It basically tells you how much of the variability in the outcome variable, like house prices, is explained by your model's input features. It's a value between 0 and 1.
So an R squared of 0.8 means your model explains 80% of why house prices vary.
Pretty much, yeah. A value of 1 would mean your model perfectly explains all the variation, which rarely happens in real life. A value of 0 means your model explains none of it. It's no better than just predicting the average price for every house.
So for regression, you generally want low MAE or RMSE and high R squared.
That's the general idea, yes. Your model's predictions should be close to the actual values, and it should explain a good portion of what's going on.
Wow. We have covered a lot of ground. Let's try and wrap this up neatly.
Okay, so we dove into machine learning's dynamic duo, classification and regression. Classification is all about sorting things into those distinct categories where bin spam or not spam, reptile or not reptile, survived or died, maybe even identifying multiple tags in a photo.
And we saw KNN uses neighborly votes, while logistic regression gives probabilities and those insightful weights that tell us why.
Then we switch gears to regression, which is all about predicting continuous numbers, house prices, temperatures, sales figures.
Using models like linear, multiple, or polynomial regression to find the best line or curve and maybe ridge or lasso to keep things simple and avoid overfitting.
And crucially, we talked about evaluating these models, not just relying on simple accuracy for classification, but using metrics like sensitivity, specificity, precision. We're called choosing the right one based on the cost of different errors.
And for regression, using MAE, RMSE, or R squared to see how close our number predictions are and how much our model actually explains.
Knowing the difference between classification and regression, knowing which tool fits the problem, and knowing how to properly measure success. That's absolutely fundamental. You wouldn't use a screwdriver to hammer a nail right.
Definitely not. And you wouldn't use regression to answer a yes-no question or classification to predict an exact price. It's about the right tool for the job.
What's really struck me, again, revisiting this, is how these tools, especially something like logistic regression on the Titanic data, don't just predict. They offer genuine insight. They quantify complex historical events.
Yeah, seeing those weights for class and gender, it turns historical observation into quantifiable factors. It really shows the why.
And that leads to a final thought. Maybe, if we can use data to understand the factors behind who survived a historical disaster like the Titanic, what other complex, maybe seemingly unpredictable outcomes could we start to anticipate or even influence if we just looked at the right data, the right features, through the lens of classification or regression?
That is a provocative thought. What patterns are hidden in the data of your own life or your work or the world around you just waiting to be revealed by asking the right classification or regression question? Something to definitely ponder until our next deep dive.